Alright, ladies and gentlemen, welcome back to Simkins Physics Corner. I just started this video and then we had a fire drill, so I'm jumping back into it here. We're looking at a conservation of momentum problem for two objects coming together to collide and stick and move off in a particular direction. So this is slightly different than our previous example when it was a deflective collision, if you will. They stayed as separate objects. So we're going to take a look at this one, and this problem is going to emphasize the importance of momentum as a vector. So let's get started. Alright, I've already drawn here, because I had previously started the problem, block A with a particular mass. You always want to convert your units into standard international units at the beginning of the problem. So instead of grams, I just wrote it as 0.230 kilograms. Traveling north, drew the vector there, with a speed of 5.9 meters per second. Alright, then we have block B. This is where we left off before the fire alarm went off. Block B with a mass of 245 grams travels west. So what I'm going to do here is I'm going to draw block B over here. And we know it has a mass of 245 grams, aka 0.245 kilograms. But it doesn't tell us the velocity of that block, and that's this problem, is what is the velocity of that block? It's going to collide with block A, so I'll draw the vector. So they're going to come together here. After the collision, the blocks move off together with a velocity of 3.64 meters per second at an angle of 50.7 degrees to the north of west. What was B's speed just before the collision? So we see we want to solve for the speed of block B here. Now, this is just a common sense thing. If two blocks are coming like this and they run into each other, of course they're going to move together that way, right? So we have this intuitive feel that we're going to be moving to the northwest-ish, some particular direction. So I'll draw my before picture over here, and I'll draw my after the collision picture over here. And of course, after the collision, they'd be moving off with some velocity. I'll kind of draw them here stuck together. Here's A and B. And I'll indicate the direction that they're headed here. This can be a little tricky, but north of west, if you think this is west and we go north of that, this angle here would be 50.7 degrees. So that's the angle they're referring to when they say north of west. We also know that that velocity is 3.64 meters per second. We know the angle. And the nice thing is, since these two objects are sticking together and we happen to know both of their individual masses, of course, as they move together, we can figure out their total mass. If we just take the mass of A and add the mass of B, we get the mass of A plus B. So let's go ahead and do that real quick, because we're going to need that. I'll just say M total is going to be MA plus MB. Okay, so in this case, we do 0.230 plus 0.245 would get us, brought my calculator today, 0.475 kilograms. So that's our mass for the after collision piece, if you will. Alright, so when we understand this problem, we know that all of the vertical momentum for the before is stored in mass A. See how B is not moving vertically at all. It has no vertical component of velocity, therefore it has no vertical component of momentum. What that means is that A's momentum is going to be giving A plus B afterwards when they stick together. Any vertical momentum that A plus B has, it has to come from block A. And similarly, any horizontal momentum that the A plus B block has after the collision must have originated or have come from the original horizontal momentum that B brought into the picture. So let's keep that idea in mind, and let's go ahead and write that down as an equation. What we can say here is that the Px, the momentum before in the x component, would be mass A times velocity of A. Right? Or in this case, it would just be 0.23 kilograms times 5.9 meters per second. So what we know is that the total, the sigma px, the total momentum horizontally before our collision, drop this into my calculator, would be the mass of A times the velocity of A, or 1.357 kilogram meters per second. So the law of conservation of momentum tells us that if this is the total momentum before the collision, then it has to be the same amount of x momentum after the collision. So that would be sigma px over here also must be equal to 1.357 kilogram meters per second. All right, now at this point I'm going to just shift up a little bit. Let me just zoom out slightly here for you guys so you can see a little more paper. All right, sorry about the fuzz there. There we go. The second thing we need to keep in mind is the y direction momentum, the sigma py. Now, of course, all of that comes... sorry, I wrote this backwards here. This should say px, or this should say py, because A, of course, is bringing the y component, the vertical component of momentum. That's py there. and this is py there. I apologize. See, I shoot these live, one take, one edit, so you get to see the full thought processes going on here. And you might make the same mistake, and that's why it's important to analyze your work as you go through. So our total y momentum comes from A, and our total y momentum afterwards from the two blocks together must be the same amount of momentum right here. So now actually we're looking at the sigma px, which comes from mass b. Now the thing here is we know mass of b, but we don't know velocity of b. That's the whole point of this problem. So this is going to be the root of where we explore to figure out, okay, what is the velocity of the block B. However, we do know that the sigma px over here, we can find that. All right? And the way we can find that is by mass total times velocity in the x direction. Now remember, momentum is a vector, which means it has magnitude and direction. And so here, if I want to find my px for my after, I'm going to use the mass, which, as you can tell, this is why drawing a picture is so important. It's just going to be the combined mass of A plus B. So we're going to take the mass, 0.475 kilograms, times Vx. All right, now we're looking for the x component of the velocity. The x component of the velocity. And since the velocity is up and to the left, our x component, or our horizontal component of velocity, would be this piece of the triangle down here. And using a little trig, you can do that Vx would be equal to V cosine of that angle. All right, so Vx would be written as V cosine of our angle, or in this case, if I go ahead and plug in all the numbers before I get your final answer here, the V was 3.64 meters per second, and it would be cosine of the angle 50.7. All right, and it looks like my face is blocking the work, so let me move my face a little bit. There we go. That's better up there. Now, some people will take a point of contention here. They'll say, Mr. Simkins, you're demonstrating bad behavior because 50.7 degrees is this angle. It's not relative to the horizontal. It doesn't go by our counterclockwise from east convention. Well, just keep in mind that since we're going to the left, that must mean, since we're going to the left, that must mean that we have a negative momentum in the x direction. All right, so I'm just going to go ahead and leave it like that, and as long as you stay consistent, you'll be okay. Let's go ahead and plug this in. 3.64 times cosine of 50.7. All right, so it looks like our x component of momentum after the collision can be rounded here to, well, let's say 0.095. Here we go, and that's kilogram meters per second. Okay. So it's at this point that some people would get stuck. They would say, well, Mr. Simkins, how in the world am I supposed to go from this after side to the before side? Well, it's actually quite simple. Let me scoot this up just a little bit for you guys so we can investigate this final piece of the problem. Now, because momentum is a vector, we know that the overall momentum of A plus B can be broken into components because momentum is a vector. Any vector can be broken into components. If we look at the overall P, the overall momentum of our after collision, we can say that that must be made up of Px plus Py. And when I say plus, I don't mean addition straight up. You, of course, would have to do the Pythagorean theorem with a squared plus b squared equals c squared to get this to come out. However, we don't even have to go there, really, because we already know the px, the x component of the after momentum. That has to be equal to the x component of the momentum before the collision. So all I'm going to do is take this number right here. You can see that that's equal to px after the collision. And I'm going to set that equal to px before the collision because momentum horizontally must be conserved. And so if I do that, 1.095 kilogram meters per second equals, all right, mass, oh good, we know that one, 0.245 kilograms times the velocity of b. And it turns out we don't even have to leverage this strategy too hard with the idea of the components of momentum. Really the only place we had to use that was here when we did cosine, of course. Cosine because this is the adjacent and this is the hypotenuse, and that would lead us to SOHCAHTOA, or cosine of theta equals a over h, or in this case cosine of theta equals to total momentum over px, which is where we derive the equation px is equal to, there's a p down here, px is equal to p times cosine of theta. All right, so that's where we used up here. I'm probably just going to delete that part of the video because it's not useful. Okay, so we have the velocity here. Let's just go ahead. I got a little off on a tangent there. and 0.245. Go ahead and divide this. You can see that the kilograms are going to cancel out, which is why units are helpful as you go along. And of course, our velocity for B would be 1.095 divided by 0.245. Our velocity here would be 4.47 meters per second. Let's just double check to make sure that we have all the information it asked us for. It did ask for what was B's speed just before the collision. Since speed is the scalar version of vector, of velocity, we don't even need a direction. We can just say, hey, the speed is 4.47 meters per second. So that's it. That's the problem. If you keep in mind that the x component of momentum before a collision must be equal to the x component of momentum after a collision, and similarly, the vertical component of momentum before a collision must be equal to the total vertical momentum after a collision, you'll be just fine. You can apply this strategy to any type of problem you see that has to do with a collision.